Bismillahirrahmanirrahim. Dear students, hope you will be fine. Today we have a third lecture of organic chemistry, and the topics which will be covered are resonance and hybridization. So, as you know that in the previous lecture we explained some background for the resonance. In that case, we explained that how the breakdown of octet rules takes place, and we explained one of the example in which, according to the Lewis structure, we have such kind of bonding. Okay, but experimental result shows that there is possibility of single and double bond, and the bond length is in between the single and the double bond. So it is impossible to explain this molecule on the basis of a single Lewis structure. That is why the concept of resonance was introduced, which can explain the different kind of structures of this kind of molecule. For example, we can write different kind of structure for this molecule, like this one. Okay. Another structure is given like and similarly, in another structure we can write this . Okay, there is another structure also, which is also which can also explain the resonating structure of this molecule, and that is okay. So that one is so this is the resonating structure of this molecule. Similarly, we can explain the resonating structure of the benzene according to the key core structure. So that is like this one. And we can also explain the resonating structure of the ozone. Okay. So such kind of phenomena is called resonance. So what is the resonance? Definition of the resonance. So on the basis of these explanation, we can define resonance as the representation of a real structure. The representation of a real structure, which we also call resonance hybrid, with the help of contributing structures, and that contributing structures are just imaginary structures, which we also called canonical forms. So the representation of a real structure with the help of imaginary structures or contributing structure or canonical forms is called resonance. This can be explained on the basis of a story, a proposed story. If a person go to the forest and he see some strange animal there. When he come back to his village, town or city, how he will explain about the strange animal, although he doesn't know, and neither other friends of him or other people know about that strange animal. So he will take the help of some other animals. For example, if he will say that his tail is like a horse, his neck is like giraffe, his head is like a lion, his body is like an elephant. So he will draw some imaginary structures, and on the basis of these imaginary structures, he will try to explain the real structure, which is not present here, but it is present in the form of a strange animal in the forest. So such phenomena is also resonance, because we don't know about the real structure of a molecule, but we just try to explain the imaginary structure, the real structure with the help of imaginary structure or canonical forms. Okay. So there are some terminology resonance which we already discussed. The resonance hybrid, that is the real structure, and the structure with the help of which we try to explain the real structure, and that is called the contributing structure, that is called the imaginary structure, and we can also say that as canonical forms. Okay, now there are some important points which we want to discuss about resonance. Okay, the first one, that the resonating structures, or we can say the canonical form or the contributing structure, these structures are not real. So the resonating structures are not real. We just take help of this structure in order to explain the real structure. Similarly, there will be no equilibrium between the resonating structure. No equilibrium between the resonating structures. So it means that the resonating structure, for example, if we have two resonating structures, then we can explain these resonating structures just by putting a double-headed arrow. While we cannot explain this in this form, because it cannot explain the equilibrium between the A and B. It doesn't mean that sometimes we have A structure and sometimes we have B structure. It means that is convertible, interconvertible. So the resonating structures, they have no equilibrium. Point number 3, resonating structures are not isomers. And you know about isomers. having same molecular formula but different structure formula, and we have different kinds of isomers. For example, if I write in a formula, for example, this kind of molecule, okay. So now in this situation, this is not the isomers, this is the resonating structure. But in this situation, so these are the so totally we just shift the position of the atom, the nuclei. So this kind of arrangement, this is on the these are the isomers of these two of the molecule, but this is the resonance. So resonating structure. So resonating structure are not isomers. Now let us discussion about the kind of the contributing structure. So we can divide the contributing structure into two. One is the major contributor and the other one is the minor contributor. So major contributor always considered as more stable than the minor contributor. So we have two kind of contributing structure. One is the contributing structure. So we have two kinds. One is the major contributing structure and the other one is the minor contributing structure. So the major contributing structure always obey octet rule, while the minor contributing structure does not obey octet rule. For example, if we take the example of this molecule, so so this molecule obey the octet rule because there are 8 valence electrons with each atom. But if we take this example, so in this situation, you see that here there are more than 8 electrons in the valence shell of the nitrogen. So which means that it doesn't obey the octet rule. The second point in this case is that major contributor have greater number of covalent bonds, while the minor contributor have lesser number of covalent bonds. For example, this one contains 11 bonds if you count, while this one bonds. So the number of covalent bond also affect the nature of the contributing structure. So major contributor have greater number of covalent bonds, while the minor contributor have lesser number of covalent bonds. The third point is that the major contributor possess minimal formal charge, while the minor contributor have maximal formal charge, that is maximal formal charge. For example, so if we take the example of this molecule, So here you see that we have minimal parallel charge. We have minimal parallel charge. Well, in this case, we have maximal parallel charge. So it means that this contributing structure is the major contributing structure, while this one is the minor contributing structure. Similarly, we can explain that the major contributing structure have less charge separation, while the minor contributing structure have more charge separation, less charge separation. More charge separation. For example, now in this situation the parallel charge are closer. There is less separation between the two charges. While in this situation there is more distance between the two charges. So contributing structure with less charge separation will be considered as major contributor, while the contributing structure which is separated by more distance will be considered as minor contributing structure. There is also another point that if we have such kind of molecules, so the molecule in which the adjacent atom have similar charges, then that kind of molecule will be considered as minor contributor because of its less stability, and because you know that there is repulsion between the similar charges, so this molecule become unstable, and then it will give us the minor contributing structure for a molecule. Another point which can be explained on the basis of the electronegativity, so in which we can say that the negative charge will be always, the negative charge will be always on more electronegative atom. For example, in this situation we have a negative charge on oxygen, while in this situation we have a negative charge on carbon. So in this situation we have a negative charge on oxygen, that is the more electronegative atom, while in this situation we have a negative charge on carbon, which is the less electronegative atom. So it means that this kind of molecule will be considered as more stable as compared to this molecule. So that is the major contributor, and this one is the minor contributor. Another important point is that the molecule will not deviate from the ideal bond length. The molecule will not deviate from ideal bond length. For example, for benzene we have three different structures which are also called D-bar structures. So in this situation we have a deviated bond length So now this bond, which is between the two carbon, this single bond between the two carbon is not the actual bond length between the two carbons. So this is deviated from the actual bond length. So the molecule which will be not considered as the major contributor are more stable resonating structure in which the bond length deviate from the ideal behavior. So this is all about the contributing structure. So we have two kind of contributing structure, major and minor, and you can decide which one is the major and which one is the minor on the basis of these points which we already discussed. Now coming to the stability of the resonance hybrid. Stability of the resonance hybrid. Stability of resonance hybrid. So the resonance hybrid stability depend upon the number and contribution of the contributing structure. So the first point is the resonance hybrid will be considered as more stable when there are greater number of contributing structure as well as the contribution of the contributing structure will be more, or we have equal contributing structures. So there are 2 points. In one, the number of contributing structure for a molecule if greater, then that molecule will be considered as more stable resonance hybrid. And the second point, that that number of contributing structure have equal contribution. So if molecule follow this kind of things, this kind of principles, then that kind of molecule will be considered as stable resonance hybrid. For example, we have two structures for benzene. So we have two contributing structure for benzene, and both of these structure have equal contribution. Similarly, for naphthalene, we have three kind of contributing structures. For naphthalene, we have three kinds of contributing structures. Okay, so these are the three different contributing structure for naphthalene. Similarly, for anthracene, we have four contributing structures. So greater the number of contributing structure, more will be the stability of the resonance hybrid. So on the basis of this, we can say that anthracene is more stable than naphthalene, and naphthalene is more stable than benzene. Okay. Similarly, we can explain the acetic acid. And acetate ion. So for acetic acid, we can write two contributing structures. One is in this form, while for the acetate ion, we have this kind of structures. So if you observe both structures, you can decide which one is more stable. So the number of the contributing structure are 2 for both acetic acid and acetate ion. Now we can decide on the basis of the contribution of these contributing structures. Now in this situation the contribution is not equal, while in this situation, in the case of acetate ion, the contributing is almost equal. That is why the acetate ion is more stable than acetic acid. And on the basis of this, we can explain that acetic acid is a weak acid. Because when we dissolve acetic acid, ionized acetic acid, convert it into acetate, which become more stable, and that is why we have a reversible reaction and we get the acetic acid back. So it means that we have a less ionization. A second factor which can explain the stability of the resonance hybrid, that is the resonance energy. Resonance energy can explain the stability. So resonance hybrid with more resonance energy will be considered more stable as compared to those which has less resonance energy. So first of all, you can define resonance energy. So what is resonance energy? Resonance energy is actually the difference of energies of more stable canonical form of a molecule and actual molecule. So the difference of energies between the more stable canonical form and the actual molecule, so that is called the resonance energy. So we can write this resonance energy is equal to more stable, energy of the more stable canonical form minus energy of actual molecule. So the canonical form can be selected on the basis of a proposed model. For example, for benzene, we always say that proposed model is 135 cyclohexatriene. So from the hydrogenation energy, the bond energy, we can calculate the energies for that stable canonical form. For example, if we take the example of this one, cyclohexene, so it can be converted into cyclohexane. And we have 119.5 kilojoule per mole energy released. Similarly, you can say cyclohexadiene, which can add 2 hydrogen molecule and can be converted into cyclohexane, and at well release energy 39 kilojoule per mole. Similarly, 135 cyclohexatriene, which we converted into cyclohexane with the energy 358.5 kilojoule per mole. So this one, 135 cyclohexatriene, is considered as the most stable canonical form of benzene. Now, we know that from experiments we have benzene, can be converted into cyclohexane along with different conditions, and the energy is 208 kilojoule per mole. Now on the basis of the formula you can write here the resonance energy for benzene is equal to the energy of the most stable canonical form, that is 135 cyclohexatriene, minus the energy of the actual molecule, that is benzene. So we will get 155 kilojoule per mole. That is the resonance energy. So this is the method of the calculation of the resonance energy. You can calculate it for other molecule as well. Now if we compare the resonance energy of three different organic molecules, for example benzene, naphthalene and anthracene, then you will observe that so for benzene we have 150.5 kilojoule per mole. For naphthalene we have 255 kilojoule per mole, while for anthracene we have 351 kilojoule per mole. Now on the basis of the resonance energy you can decide which molecule, which resonance hybrid is more stable. So it is clear that anthracene is more stable as compared to naphthalene, and naphthalene is more stable as compared to benzene. The last topic in this resonance is the resonance effect. Resonance effect. So what is meant by resonance effect? We can explain this on the basis of a molecule NH3. Now in NH3, the lone pair of electron is localized on the nitrogen atom. So it cannot be delocalized. But if we react ammonia with benzene, then we will get a molecule called aniline. And this molecule, the lone pair of the nitrogen, will be delocalized throughout the ring, and we will get less charge density on the nitrogen and more electron density on the ring. This effect, in which there is decrease in one position while increase in another position, this such kind of effect is called resonance effect. So we can define the resonance effect as the decrease in the electron density, at one position or at one point an atom or molecule with the subsequent increase on another point, on another position or point of a molecule. Such phenomena is called resonance effect, which is also considered as mesomeric effect. So resonance effect is also called mesomeric effect, and we always represent this one by capital M. We will discuss this positive M and negative M. So On the basis of this, we can classify the mesomeric effect or resonance effect into two kinds. One is called the resonance effect by electron donating groups. So that is the electron donating effect or electron donating mesomeric effect. So the first one case is electron donating resonance effect, and that is that the value of the M is positive. So the molecule which has more electronegative atom or having unsaturated system, molecules with more electronegative atom connected with unsaturated system always create electron donating resonance effect. For example, NH3 O minus, NR2, NHR, and many others. You can say this NH2 bonded. Okay. The second one is the electron with drawing resonance effect. But first of all, we have to explain electron donating resonance effect. So, for example, we have NH2 bonded with a ring. Now, in this situation, the electron will delocalize from the ring, from the nitrogen towards the ring, and we will get different kind of structures. In the next structure, the electron can be taken by nitrogen and we can get the first structure. So this is the electron donating resonance effect caused by the NH2 group. The electron withdrawing resonance effect. Electron withdrawing resonance effect, that is negative mesomeric effect. So such kind of effect can be caused by molecule with multiple bonds having more electronegative atom. So molecule with molecules with multiple bonds, you know that, double or triple bond, and more electronegative atom. For example, nitration of benzene can be takes place in the presence of nitric acid and sulfuric acid. Okay. Now the electron will withdraw from the ring So in this situation, the electron density on the ring decrease. So this is called the electron withdrawing resonance effect. Other example for this is NO2, CN, and many others. Now, effect of the resonance effect on the properties of compound. So what are the implications of this effect? How we can explain some properties of the molecule on the basis of resonance effect. Effect of mesomeric effect, or we can say relation of resonance effect with properties of compounds. So first of all, we can explain the acidic strength of a compound, acidic and basic strength of a compound on the basis of resonance effect. For example, if we take the example of ethanol, so ethanol can ionize in water and will gives us this kind of ethoxide ion. Now the pKa value for this is 70, which is much higher. It means that this is weak acid. And you know that pKa, so pKa is inversely related with the Ka, so greater the Ka for acid, more stronger will be the acid, and greater the pKa value, less will be the strength of the acid. Now if we take the example of phenol and we dissolve it in water, so it will give us phenolate ion, and that phenolate ion is stabilized through resonance effect. For this, the pKa is equal to 10. So it means that phenol is more stronger acid than ethanol. This can be explained on the basis of the stabilization of phenolate ion through resonance effect. We can explain this in this form. We have phenol, and if it dissolve in water, it will gives us phenolate ion. Okay. Now, because we know that the OH group is electron with donating group, so it will donate the electron to the ring, and we will get different contributing structure for this molecule. Okay. The next structure is so the electron density distributed throughout the ring, which stabilize the phenolate ion, and that is why phenol is more acidic. Now, if we add another electron withdrawing group with the phenol, what will be the effect? Either the new molecule will be more acidic or less acidic. What we expect? For example, if I add nitro group to a molecule, nitro group, and we have nitro group. Okay, so the nitro group will draw the electron from the ring, and it will make this phenolate ion more stable as compared to only phenolate. So we will get okay. Okay. So there are different kind of structure on the basis of which we can explain the stability of the phenolate ion. So now if we have more nitro group, in this case we will get more stronger acidic substance. For example, if we compare the substance with this pKa value, so we have phenol with pKa value of 10, we have ortho nitro phenol with a pKa value of 7.23, or para nitro phenol has a pKa value of 7.15, meta nitrophenol has a pKa value of 8.35, and 2,4 dinitrophenol has a pKa value of 4.07. So you can see from the result that 2,4-dinitrophenol is the more acidic substance as compared to other, because it contains two nitro groups which have greater electron withdrawing effect, and that make the molecule more stable. Okay, we can explain also the basicity of a molecule on the basis of the resonance effect. For example, if we take the example of the NH2 and aniline. So what do you expect? Which molecule is more basic? Okay. Which molecule is more basic? You can think about this, because you know that here the lone pair of the electron is available to nitrogen. It means that this one is more basic than aniline, because the lone pair of electron, as we already discussed, is delocalized throughout the ring, and that is why it is not available for donation. That is why this aniline is less basic as compared to ammonia. And further its basicity decrease because of this nitro group, which further withdraw the electron from the NH2 group and become and make it more and make it less basic as compared to NH2 and as compared to NH3. So this is all about the resonance and the resonance effect. I hope you will enjoy this. If you have any question about this, then you can ask me, and you can comment in the YouTube comment section, and I hope I will try my best to satisfy. Thank you.